I've not started with a picture of a tall building, I've started with a picture of a car factory. And there are two reasons for that. One is I'm going to talk a bit about manufacturing. The second is that in the UK at least, the construction industry is always being compared, and not in complementary ways, to other manufacturing industries such as the car industry, aviation and so on. And our government and our investors say that we're poor value for money, we're wasteful, we have a poor health and safety record, and we lack innovation. So this talk is really about how we at Laing are trying to address those criticisms and adopting a philosophy which we call design for manufacture and assembly. And you might know some other term, because I'm sure it's more general than those specific words. And as I said, it's a concept that's derived from manufacturing, so it's something that you can observe in the automotive industry, shipbuilding, aviation. But it's not just simply prefabrication, and it's not just simply doing things off-site, because if you think about shipbuilding as an example, shipbuilding has changed tremendously in the last 50 years. But they've always built ships not in the water. They've always built them in shipyards. But the way that they've thought about how they put the ship together, that's the key. So just a bit more on their philosophy, talking about manufacture. If you talk about the manufacture of anything, or the production of anything, including a building, a light bulb, a jet engine, it could really be simplified into it's just the addition of materials, parts, and labour processes. And what great manufacturing does is it imposes a great deal of logic on the way those things are put together. And it builds a hierarchy in the way things are put together. So on the left here, that's just a simple hierarchy of how things might come together. And at the moment, on a building site, all these things might happen and come to site at the same time. So you might get raw materials, concrete, wet concrete arriving one day. You might get a lift motor room, which is quite a sort of high-level pre-manufactured item arriving the next day. And actually, that's not very efficient. And also, one person's final assembly in manufacturing might be another person's part. So the jet engine is the final product for Rolls-Royce, but it's only one part for Airbus. So that's a fractal, because that's got the same sort of recursive geometry. So here's Airbus. This is their final assembly plant in France, where they're putting together an A380 aircraft. And many of those large modules have come from separate factories all over Europe. And that's the way that they've managed to sort of improve their process. And it's the same thing that's reflected in the shipbuilding and in the automotive industries. So what they've all got in common is that the final assembly is usually quite a simple process. Every production line is quite simple, rather than trying to do everything on one production line in one place. So what we're saying is, can't our construction site be like a final assembly factory? And we do all the hard work in other factories. And we've tried to implement this on the Leadenhall building, and it's generated some interesting statistics. I think we cut our on-site labour by 40%, and we also were able to offer the client a programme saving of 38 weeks on site. Obviously, in the centre of London, anything that you can do to reduce the amount of work that's happening in your urban environment is quite important. And actually, before I arrived at the conference, I thought the Leadenhall building was quite a tall building, and he's actually down here on the wall. He's only small, but it's an essay in sort of steel fabrication and a celebration of engineering. There's no concrete core; it's all steel megaframe structure. So 2 prerequisites for a DfMA approach. One is logistical. You're obviously going to be handling some bigger than normal components, so you need to get the biggest cranes you can lay your hands on. And the other thing you need is a really well-functioning digital model. We call that digital engineering, and it's not just that we use it as a design tool to detect clashes and so on. It's actually used as a manufacturing tool to control manufacturing processes and also to control logistics and identifying components and so on. So there's a snapshot from our digital model in the bottom right and a couple of photos. So our steelwork, again, we try to deliver that in as big a pieces as we can. It's all made in a factory. There's no site welding. Components are bolted together on site. Even though we made the pieces as big as we could, there were still more than 11,000 of them. Columns up to 26 metres long, weighing 60 tonnes. And obviously all the workmanship is in the connections, in the nodes. Another nice picture of the construction, a node being lifted. And on the left, again, an image from our digital engineering model showing how it's used to plan construction. So the elements highlighted in colour are the elements to be erected in a particular shift, and the digital engineering model is used to sort of to model the construction process in the virtual world, so you can test out different orders, sequences, and so on. Concrete also, as I said, it's mainly a steel frame building, but obviously the floors are concrete, and there are also some stair cores that are concrete. Adopting the DfMA approach means that we don't bring wet concrete to site. We bring precast concrete, highly engineered, individually made precast elements that are the right shape, have the right fittings to marry with the steel frame. And actually the floor system was one of the achievements which we were most pleased with. Just for comparison, this is the traditional approach, and if you think about the DfMA philosophy, this is bringing lots of small parts to site, shear studs, metal decking. It's almost bringing a raw material to site, which is the wet concrete, and doing all that work on site isn't necessary. So here's some more images. I think the next few slides are about our floor system. It's a precast floor system. It forms composite beam design, so it needs to be stitched together and also have a shear connection to the steel beam. But you can see there's very few operatives on site. Panels are just lifted in. They've got their edge protection prefixed. The floor can support a cherry picker, bottom right, immediately. You don't have to wait for the concrete to cure before you can start loading the floor. So in detail, the plank is a fairly traditional rebar cage. It has some dowel bars that were connected through tabs on the top flange of the steelwork. And again, the digital engineering model was essential in order that when we landed the planks on site, the dowels went through the right holes in the steelwork, because trying to do that without the model would have been impossible. Just some more slides. This one's just highlighting that the floor plate obviously is more than a gravity load carrying element. It's forming the diaphragm in the building, and any building with a mega frame has particularly intense diaphragm forces at the mega levels. So we had to cater for those. Some images from underneath, precast soffit with cast-in channels, because we were trying to mimic the facility that a metal deck gives you. And of course, to implement this product, we had to go through the appropriate testing and approvals process. But that wasn't our only DfMA strategy for the building. one of my favourite areas of the building is called the North Core, and it's the steelwork that's in yellow, and that's one of the reasons it's my favourite part of the building. But also, it's an exceptional piece of DfMA because it really embraces the idea of bringing things together into sort of quite well-developed modules before they're brought to site. So each level of the North Core was made of 3 components, and the next picture shows an exploded view of one of those components. So the component was the yellow steel frame, which is the columns and the beams and the bracing, onto which we landed a separate M&E module, and then on top of that we landed precast concrete planks. So each one of those sub-assemblies was made in a different factory in the UK. They were brought together to form one module, and then transported into London on one wagon. So on the bottom left you can see one of these modules being lifted. So in one lift you're installing your columns, your beams, your MEP and your concrete slab, which is just incredibly efficient. And the North Core could have flown up in a matter of weeks had it been stable. It needed the rest of the building to lean on, but another example was at the very top of the building. Obviously, the building leans as it gets towards the top in order to preserve the view of St Paul's Cathedral. So they decided to put the plant rooms all in the roof of the building. And again, we wanted to use our digital model in order to squeeze the plant rooms in as efficiently as possible and maximise the available space for the client. But we also had to plan how these modules could be sort of shoehorned into the building and moved around. So looking at the DfMA approach, the total building is a sum of several systems: the steel frame, the concrete planks, the facade and the MEP. Bottom left you can see one of our MEP modules being lifted up to the roof. Top in the middle is the digital engineering model of the MEP, and then on the right hand side it's a vertical MEP module for vertical risers and so on. And then just finally a word on the facade. Because we were using our cranes so intensively to lift steelwork and precast components, we wanted our facade to be installable without relying on the cranes. So we developed a special materials handling system that could sort of climb up the outside of the building, and we could pass it the glazing units, and it could sort of trolley those around on the outside for installation. So in summary, the Leadenhall building has been, I think, to date, Laing O'Rourke's most deliberate attempt at DfMA. We've realised real benefits from doing it, and we hope to carry on changing the way we build things in the future.